Recently, we've talked about the motion of a photon in a Schwarzschild gravitational field, and after a great deal of effort, we figured out what the equation of motion is. We investigated the case where the orbit was a circle. The u quantity in this equation is 1 over r. We figured out that you can get circular orbits when r equals 3 gm over c squared, and not any other place. If you're wanting to look at the path of a photon that is not a circle, then you have to deal with this differential equation, and there's bad news. This equation is too complicated to solve in any nice closed form way. We'll see what we can do about that in a moment, but in the meantime, I want to fix my units up. For a given problem, I'm going to change my unit of mass so that g times m is equal to 1. Also, I'm going to continue using units for time so that the speed of light is still 1 as well. This makes my differential equation look a little bit nicer. Also, in these units, I have the location of both the event horizon and of the photon sphere. Likewise, in these new units, the location of the photon sphere is r equals 3. Later, when I draw pictures of the paths of photons, I'm actually going to include a rough picture of r equals 2 and also r equals 3. When we get inside r equal 2, that means we've fallen into the black hole. Now, of course, a second-order differential equation of this type generally has a two-parameter family of solutions. I'm going to have to supply two additional facts in order to get a specific solution out of this. At least to start with, I'll suppose that u, when theta equals 0, is equal to some constant alpha. That means that at theta equals 0, r is 1 over alpha. I'm also going to assume that u prime at theta equals 0 is 0. If I'm thinking of having some sort of orbit, then this means that u, and therefore r, has either a local minimum or local maximum at theta equals 0. I'm either putting the closest or furthest point away at theta equals 0 by doing this. As I said, though, this differential equation can't be solved in closed form. Luckily, there are a wide variety of high accuracy numerical methods that a person could use. The strategy that we're going to follow is to convert our problem into a system of first-order differential equations. Once we've done that, we'll use Runge-Kutta or some other high accuracy method to solve the resulting problem. I'm going to introduce two new variables, y1 and y2, which make up the components of some vector y. Secretly, y1 is the u variable, and y2 is the derivative of u with respect to theta. As usual in this kind of situation, we'll define the derivative of vector y to be the derivatives of the components of y individually. But since y1 is u, the derivative of y1 is the derivative of u. y2 is u prime, so the derivative of y2 is the second derivative of u. But the derivative of u with respect to theta is y2, so I can write that down. All I need to do to convert my problem completely over into y quantities is to do something about the second derivative of u with respect to theta. If you look at the differential equation at the top of the page, though, if I simply subtract u from both sides, I'll have the second derivative of u with respect to theta isolated, and this is how I'll put my mathematical problem into my computer program. I've written code to carry the preceding plan out. In each case, I'm going to read input from a file. The things that are read are the initial theta value, the ending theta value, the number of steps to take in the method, and the initial values of u and u prime. In case I hit the singularity, I have code in place to stop program execution. By singularity here I mean r equals 0. Also, in order to get pictures that are reasonable looking, I automatically stop program execution whenever the r coordinate becomes larger than 10. In this example, I start on u equals 1/3. Those of you who are wondering where that 1 came from, take Math 4670, and I'll tell you all about it. I'm doing 0 to 13 radians, which is 2 orbits about, and dr d theta, and therefore du d theta, are 0 initially. The inner circle of dots is the event horizon. The outer circle of dots is a set of points that lie on the photon sphere, and the blue graph is the computed orbit using my numerical differential equation solver. As you can see, this looks quite good. I have an output file that shows theta versus the radial coordinate. I want to have a look at that just to make sure. As you can see, early on at least, the radial coordinate is 3 and doesn't appear to be changing at all. I have 1,000,000 lines in this file because I did 1,000,000 steps, so let me jump forward 250,000 steps. At 250,000 steps, the radial coordinate is still 3 to all intents and appearances. Let's jump forward another 250,000. The same situation occurs at 500,000. I've now done just a little bit over 1 orbit, and as far as the computer can tell, r is exactly 3 still. Same story after 750,000 steps, and jumping to the end, it appears as though my numerical code has done extremely well describing the path of this photon in its circular orbit. I'll run example number 2. In this one, I made du d theta slightly positive. Because of the relation between u and r, that means that dr d theta was slightly negative. I was on the photon sphere, but I had a very small component of motion inwards. The value of u is not a number, which is the signal in my program that it's time to quit. I indicate that if that number is nan, or the infinity symbol, we have hit the singularity at r equals 0, and this is the operating system complaining about the nan. In terms of the picture, initially we are on the photon sphere. As we proceed, though, things begin to change. Here, we are definitely inside the photon sphere, but we are still outside of the event horizon. At this stage, if the photon collided with a dust particle or something, it could still end up being reflected outward and escape. Things continue. Here, we are outside the event horizon, but not by very much. Here, we are at the event horizon. Despite what the time stops at the event horizon of a black hole people might say, as the angle continues to increase, r continues to decrease, and we reach r equals 0 in a finite amount of theta. It might be informative to look at the r coordinate file. Initially, the r coordinate stays close to 3. After 100,000 steps, though, it's down to 2.86. That's still pretty close to 3, but it's noticeably less. At 200,000 steps, the radial coordinate is down to 2.56. At 300,000, the radial coordinate is down to 1.81. We have already crossed the line. We've crossed the radial coordinate r equal 2. We're inside the black hole now. Even so, if you look at it, I'm only 59% way through this file, so I'll go up to the top and then drop down 400,000 lines. Things are beginning to go sideways in a serious way now. We're only 0.64 R units from the origin. $500,000 lines in, we are very close to R equals 0. The R value is 5.1 times 10 to the negative 5. I attempted to go 600,000 lines into the file, but it isn't letting me. Let's back up a little bit here. The radial coordinate is decreasing. It's on order 10 to the negative 7. Now, initially, theta was negative 6. I did that to plot a variety of theta values. At the very end, theta has gone from being -6 up to slightly positive at 1.02 times 10 to the -2 power. So we've made almost a complete orbit, but at the time we end up doing that, r has become 0. 1 over r is undefined. U equal 1 over r is a nan, not a number, and this is where we stopped. Notice though, at a certain point, things really went downhill quickly. 10 to the minus 9s, 10 to the minus 10s, 10 to the minus 12, and then all of a sudden, 10 to the minus 18, 10 to the minus 41, 10 to the negative 133 power, and then literally 0. I made du d theta slightly negative, meaning dr d theta is slightly positive. Starting on the photon sphere, I don't even get one orbit out of it before it heads off to infinity. This piece looks like a piece of a hyperbola. Hyperbolic. Death spiral. I didn't quite run it long enough to reach r equals 0. In this one, u is very slightly bigger than 1/3, meaning that r is very slightly less than 3. If you just look at this, you think that you have a stable orbit, but that can't be right. So let's rerun this by making the maximal theta value bigger. Death spiral. I started inside the black hole this time, and I got what looks to be about half of an orbit, and then slam into the singularity. Spiral of doom. Spiral of doom. Based on these experiments, I guess we can come to the conclusion that even though there are circular photon orbits, they're unstable. The least bit of departure in one direction or another either leads to a hyperbolic type escape orbit or a photon death spiral of doom. It might be interesting to do similar calculations and program runs for particles that have non-zero rest mass. Maybe I'll do that. In any case, I hope everyone's having a good day. I'll talk to you again soon.